Alright, so we want to prove that these two sets are the same. That the G intertwining linear maps from V to W are precisely the fixed points of HOM C V W under the action of G on it. And so by G action here, we're actually referring to the representation. So I'll be more explicit by what we mean by a fixed set, the fixed set under this G action, or the collection of fixed points, whatever. Anyways, so first I like to write out my homomorphism. So let rho v, rho w be representations of v and w on G. Okay. Also, what I'm going to do is I'm going to make this hom G here is going to be equal to hg, and hom C VW is going to equal hc, just because I don't like writing a lot of stuff if I don't have to. Okay, so see here, then G acts on HC by the representation. No, okay. Representation rho hom. Again, rho hom goes from G to HC. And so let's see here, which satisfies, and then for all V and V, G and G, and F in HC. This is just a reminder of the definition. We're going to call it rho sub H instead of rho sub hom. So we'll do that. Just because I can save two whole letters that way. Okay, so rho hom GF evaluated at V is rho W of G evaluated at F of rho VG inverse V. Okay, so now suppose F is in HCG. So this is the fixed points of HC under G. And what we want to prove is we want to prove that HCG is equal to HG, i.e. if we take an F in HCG, we want to prove that's in HC, and then next we're going to take an element of HC and prove that it's in HCG. So take an element of HG, prove it's in HCG. Okay, so anyways. So by the way, this is HC with the G outside of it. So if we wanted to be super explicit, we would write it like this, but I'm not going to do that for the rest of this problem. Okay, so what does this mean? This means that for every single G in G, rho HG of F equals F. That's what it means for, so F is fixed under the G action for every single G. So, yeah, that's what this means. So now we want to prove that F is in HG. So I claim F is G intertwining. And we know automatically that F is in HC because that's what it means to be an HCG. It means that it's in HC and it's stable under the action of G. Or it's fixed under the action of G. So all we need to prove is that homomorphism thingy. So here to this end, let G be in G and V be in V. Then, what happens when we take rho WG composed with F of V? We want rho WG composed with F to be equal to F composed with rho V of G. That's what it means for this map to be intertwining. And so let's evaluate this at some V and see if this works. So anyways, we write this out, and we just follow our nose, sort of. So we just kind of write everything out. So this is the definition, because that's just using... Okay, so here we're using the property that F is in HCG, because we have this equality. We know that F of V is equal to rho HG of F, and... wait a minute. Right, we know that F is equal to rho HG of F, and then we know by the before that rho HG of F is defined to be precisely this thing. And so... Wait a minute. Okay, phew, I think I freaked out a little bit, because I was like, oh no, I did something wrong, and I just turned this in on homework, so now my homework's wrong, and now I'm going to fail the class, but no, it's okay. So this is because we're taking F and we're replacing F with rho HG of F. But we can replace F with rho HG of F for any G we choose. So in particular, we could replace F with rho HG inverse F, because there's nothing stopping us from replacing F with that particular G. And so all we're doing is we're switching from this F to this thingy over here, and we're just choosing G inverse to put on the right hand side. So anyways, we have this, and so now we can use the definition of this rho of rho H, and it becomes rho W of G inverse, and then we have F of rho V of G of V. Okay, but now this is these rho W's cancel out, and so all we have left over is F of rho V of G of V, and of course here this is just F composed with rho V of G of V. So since this holds for all V and V, we know that rho WG composed with F equals F composed with rho V of G. And since this holds for all for all G and G, F is G intertwining. So what does this tell us? So this tells us that this holds for every single F in HCG. And so HCG is contained in HG. Yes, HCG is contained in HG. Alright, so that's good. So we got that. So for the reverse inclusion, we're going to suppose that F is in HG. And we're sort of going to work backwards. So this means that for all G and G, rho WG of F is going to be equal to F composed with rho V of G. So then for all G and G, and V and V, we have another computation. Hooray! Okay, so what are we going to do this time? So here, we're going to sort of do the same exact thing we did before, but start at a different place. So rho W composed with rho H of G inverse of F of V, well, just using the definition of rho H, we write this whole thing out. And so then this, we have the rho W's canceling out because rho W is a homomorphism. And so this is equal to F composed with rho composed with V, G of W of V. But since this is intertwining, we know automatically that this is rho VG composed with F of V. So applying rho WG inverse to both sides yields rho H G inverse F applied to V is equal to F of V. Since this holds for all V and V, we know that F is equal to rho H G inverse of F. And then finally, since this holds for all G and G, we know that F is in HCG. And this holds for all F in HG, and thus HG is contained in HCG, and hence HG is equal to HCG. And that's exactly what we were trying to prove, and so now we are done with the proof.